it means that delta F is greater than equal to 0. And PF is greater than equal to F. So if H1 and H2 are superharmonic, then also H1 mean H2. And this is a good way, because if you work on these properties, you can also create a Hilbert space of some harmonic functions, and you can work on that to create good propositions that could be useful. And so if h of x is equal to h1 of x, then h of x is equal to h1 of x, which is greater than px and y, h1 of y, mu of y, which is greater than equal to px and y, h of y, mu of y. So if G is super harmonic, then we can write that the expectation of G of xn condition on xn minus 1 and x0 is equal to y, the probability that xn minus 1 and y, G of y, mu of y is equal to probability gxn minus 1 is less than G of xn minus 1. So Gxn is super martingale. Let's talk about a proposition by an Irish engineer. His name is Gordon Foster. That's why we call it Foster criterion. It says that if A is a subset of V is finite, then gamma and mu is recurrent. This is recurrent if and if there exists a non-empty function h, which is superharmonic in V minus A, and satisfies that the cardinality of all x which h of x is less than m, this is less than infinity for all m. And because it is really related to the work of Lyapunov, Lyapunov theory is very popular in nonlinear control theory. So I should say, what is a Lyapunov stable point? So if you are a researcher in nonlinear control theory, it's just easy for you. You know that. But just to recall for some probabilists and computer scientists, so X of E is Lyapunov stable. So for example, you have some equilibrium and you're always around this. You don't go out and you don't become infinity. And traditionally mathematicians like to work on center manifold, stable manifold, unstable manifold, and these classical things, which locally shows the qualitative behavior of a dynamical system near the equilibrium points. And so Lyapunov was working on that, and you see that XE. So we say XE is Lyapunov stable if the solutions that start near the equilibrium point stay near XE forever. So this is the concept of Lyapunov stable point. And because I was talking about Foster criterion, let's talk about Foster theorem and why it is related to this kind of talk. So consider an irreducible discrete time Markov chain, an uncountable state space S. So having a transition matrix P, and Markov chain is positive recurrent. So it is positive recurrent. So if you don't know what is positive recurrent, I should recall that it exists a pi such that the limit of when n goes to infinity of summation over k to n of xk equal to x is equal to pi of x, a sure probability. And so it says that Markov chain is positive recurrent. The theorem says if and if there exists a Lyapunov function from S to R. For example, in control theory, they talk about quadratic functions because it has a good positive property that you use it for Lyapunov function. So if there exists such a Lyapunov function such that v of I is greater than or equal to 0, and for any I in S, it satisfies Pij Vj is less than infinity for I in F. And Pij Vj, if j summation over S, always summation over S, is less than or equal to v of I minus epsilon for all I which is not in F. For some set F, so examples, if it is I is outside F, it comes here and it stays around. And now you see what are the relationship between those things to probability. So let's go back to those electrical networks that I was talking about. As you know, the power dissipation of an edge is v squared over r, which is f of y minus f of x squared mu xy minus 1. So let D be a subset of V, and suppose we impose, so we have a domain D, and we impose f of x equal to 0, and this is just a subset of V. And here f of x is just f0 of x. So on the boundary of D, we have f of x equal to, on the boundary it is f0 of x. So what we are going to do is we say that, so suppose that this potential f0 that I said, this f0, and allow currents to flow into the D. Allow these currents to flow according to Kirchhoff laws for conservation of current. And so divergence of gradient of f is equal to 0 because it's Laplacian. And so f is the solution to this one. F of x is equal to f0 of x on v minus d. This is just the boundary of D. And delta f of x equal to 0 on D. So the theorem says that phi of x, let phi of x to be the expectation. If we start from x of f0 of x tau D, remember this is the exit time from D, times indicator of, we make sure that it is less than infinity, then phi is a solution to this. Phi is a solution to this equation. So to prove this, that phi is just a solution to that, we say that if x is in D, then by Markov property, we write that phi of x is summation over x of f0 of x tau D, and x1 is y, and tau D is less than infinity. So summation over y. And then what is expectation of x tau D? It means that it is just using the transition probability x and y, And now we start from y. So starting from x goes from starting from y because we use the transition probability. We sum over all of these things. So instead of going from x to outside, first we go somewhere which is y. For example, y could be here, y could be here, y could be here. So summation is over y. And from there we say that f0 of x tau d. So these tricks I have repeated several times. So it's another way about harmonic functions. That's why everybody uses for to prove the similar things. So many of these things are very similar to each other because we are just using Markov property, and even not strong Markov property, simple Markov property. So this is the proof of that. And the second part of the theorem says that if D is finite, then phi is unique solution to that equation. Phi is unique solution. And to prove uniqueness and those things, you know the typical trick. We say that, let's say phi prime is another solution. So H, you know that if phi is harmonic, phi prime is harmonic, plus and minus of them is harmonic as well. So this is harmonic inverse. So it is 0 on V minus D, and you just know that I told you that maximum principle is important. Now you can use it. You use maximum principle and say this H should attain its minimum on the boundary of D, and hence H is 0. What does it mean, H is 0? It means your phi is unique. And the third part of this beautiful theorem says that if the probability of starting from x and tau d is less than infinity is 1, we are sure that it is finite, then phi is the unique bounded solution to that. So not only a unique solution, it's a bounded solution to that. And the proof is again simple. We say f0, because f0 is bounded, phi is bounded, so phi prime is another bounded solution, and hence the typical trick, phi minus phi prime is bounded. Then you know that this is a bounded martingale because h of x n. And then because we have a martingale, when you have a martingale, what comes to your mind is apply optional sampling theorem, and then just apply optional sampling theorem. And tau d if you apply optional sampling theorem at some time, such as tau d, we have h of x equal to expectation of m0, and this is just using the optional sampling theorem. And this is a martingale, so we sample it as tau d, and this is 0, and so h is identically 0, and we have proved the third part of the theorem as well. And now let's talk about generalization of the ideas that I promised you about that effective resistance. So if we have a set B0 and it is a subset of A. So if we have A here, so A minus B0 is here, and we have another set B1 here, but all of them are a subset of your vertices of a graph. And if you imagine this, what I want to do is that there is a flux. We have a flux. Because I studied fluid mechanics in aerospace engineering as well, so all of these make sense for me. This is just a flux from going from B1 to B0. And let's talk about transience and recurrence. If B0 and B1 were the disjoint non-empty sets that I showed you, and I showed you that D is just V minus B0 and B1 this is finite. And we use a trick that say F0, our function, is just 1 if you just restrict it on B1. And phi be unique solution to, so phi is defined by F0 of x at the boundary when it goes out. And we make sure that tau d is less than infinity. So it is bounded. So let's let phi be unique solution to this equation. F of x is equal to F0 of x if you are on V minus t on the boundary. Sometimes we call it exterior boundary. And delta f of x is 0 on D. And then phi of x is probability that time to hit B1 is less than time to hit B0. It is general because even if you start inside B0, it's just return to B0. So hitting times is general. And so if I is gradient of phi, divergence of I of x is mu x Laplacian of phi of x. And the interesting things is divergence of I of x is greater than 0 if x is in B0, and divergence of I of x it is less than 0 if x is in B1. And using the lemma that I forgot to say is that the lemma just says that if I is a flow on V with finite support, then divergence of I of x is 0. If you just if your summation is over all of your vertices, don't forget this point. So this is a lemma. I want to use it for the proof. So I was saying that the divergence of I of x, x and v is equal to x on A divergence of I of x. And this is equal to x summation over A of I of xy. And this is equal to minus the same thing here, I yx, not xy. So this is just the minus of this. And this is minus divergence of I of x. So this is just a simple proof of this lemma that I need to use. So I was saying that the net current flow between B0 and B1 is called flux of I. And that is the summation over divergence of x in B0, which is minus divergence of I of x, x in B1. And this is minus flux of, just definition of flux, I of B1. So these things we may need it. So a definition, so we generalize that a finite network effective resistance between B0 and B1 to be R of finite network effective resistance between B0 and B1. So B0 and B1. You have seen that we defined 2 lectures before that the effective resistance between these any 2 nodes is Rf of, for example, x and y. But instead of 2 points, 2 atoms, we have 2 sets. So it's more general version of that. So effective resistance of that is by definition, if you have this definition, that then it will be a good generalization of that. And this is just the current flow from B0 to B1. And you know the potential of